And in order to explain why the electron is actually restricted to certain orbits in the atom, de Broglie suggested to just apply the same concept of wave-particle duality that we introduced when we discussed the nature of light to electrons. So in the same way that light is a wave that sometimes behaves like a particle, you can think of the electron in the same way as a particle with a wave-like property. It's a particle that moves in a wave type of motion. And the wavelengths of that motion of the electron is actually related to its momentum. So the momentum of the electron, which equals, according to the classical physics, the mass of the electron times the speed, is gonna equal Planck's constant divided by the associated wavelengths of the wave motion of that electron. Or in the other, if you rearrange it, the associated wavelengths of the wave is gonna be proportional to the momentum of the electron. And that's a really important idea here, because it doesn't only help us to explain why electrons inside the atom are restricted to certain orbits. It's gonna, as we will see, is gonna play a very important role in developing a lot of important technologies, as we will see in a minute. So let's just emphasize that concept of wave like motion of particles and see how the mass and the speed of a moving particle is gonna control or determine the wavelengths associated with it. So if we wanna compare or calculate the wavelengths of a particle in two cases, if you have a tennis ball that moves with this speed right here, or in meter per second with this value right here, and you want to calculate the associated wavelengths, if you know that the mass is this value right here, okay? And we want to compare this to an electron that moves at the same speed. Here we summarize the data that were given in the problem, which was the speed of both particles as 68 meters per second, and the mass of the tennis ball with this value right here, and the mass of the electron with this value right here, and also we'll need Planck's constant for our calculation. If you analyze joule per second unit, you will find that it actually equals kilogram meter square per second. So Planck's constant can be expressed as 6.63 times 10 to negative 34 kilogram meter square per second. That is going to prove really helpful in simplifying the calculation. So let's start by calculating the wavelengths associated with the tennis ball. According to de Broglie's formula, is going to equal Planck's constant divided by the mass times velocity for the tennis ball. It's going to equal 6.63 times 10 to negative 34 kilogram meter square per second. And you divide this by the mass right here, which is 6.0 times 10 to negative 2 kilogram times the velocity given right here, which is 68 meter per second. So you will clearly see that kilogram will cancel with kilogram, second will cancel with second, meter will cancel with the square, and it will be left with a number in meters, which is basically the wavelengths. And it's gonna equal 1.62 times 10 to negative 34 meter, or if you wanna express it in nanometer, it's gonna be times the conversion factor between 1 meter and nanometer, which is 10 to the power 9. So it's gonna be 1.62 times 10 to negative 25 nanometer. And for the wavelengths of the electron at the same speed, we will just repeat the same calculation using the same formula. So it's gonna equal Planck's constant, 6.63 times 10 to a negative 34 kilogram meter square per second, divided by the mass of the electron in kilogram, which is 9.1094 times 10 to a negative 31 kilogram, multiplied times the speed, which is 68 meter per second. So again, kilogram will cancel with kilogram, second with second, meter with one with the square, and you will be left with a wavelength in meters, which is gonna be 1.07 times 10 to a negative 5 meter. That significant elongation of the associated wavelengths is a result of the significantly smaller mass of the electron. So the associated wavelengths is going to be actually controlled by the mass of the moving particle and the speed of the moving particle as well. And that, as we will see in a minute, is going to prove really, really important in developing a really important technology, which is electron microscopy. If we take an electron and accelerate it to a speed that is up to 9.38 times 10 to the power 6, which is kind of a fraction of the speed of light, what would be the characteristic wavelengths associated with this electron in this case? We'll see if we calculate it. So according to de Broglie's formula, is going to equal, again, the magnitude of Planck's constant, 6.63 times 10 to a negative 34 kilogram meter square per second, divided by the mass of the electron, which is 9.1094 times 10 to a negative 31 kilogram, times the new speed, which is 9.38 times 10 to the power 6 meter per second. So carry out the calculation and you will get a wavelength of 7.7 times 10 to a negative 11 of a meter, which is basically on the scale of 1 angstrom. If you convert it from meter to angstrom, you will find that it's almost 1 angstrom, which is basically the same size of an atom. The significance of this is that when you accelerate the electron, you're able to decrease its associated wavelengths to almost the size of 1 atom. And that's really, really significant, because when you try to see something, you will only be able to see as small as the wavelengths you're using in your microscopy. So an optical microscope is gonna be using the visible light, which is usually around a wavelength of 500 nanometer. So it's not gonna see any object that is smaller than 500 nanometer. But if you use a beam of electron to see something, it's gonna enable you to see objects all the way down to 1 angstrom, significantly smaller objects in size. And that's basically the main concept of the electron microscope. What you actually do is you use an electron beam, accelerate it to a speed to the magnitude that we just calculated, and then hit the objects that you are trying to see, and it's going to be able to magnify the objects all the way down to 1 angstrom, which is one atom. So it's actually able to picture one atom in the picture. This is a picture using specifically the tunneling electron microscope for one atom or a set of atoms. As you can clearly see, very distinguished atoms of carbon monoxide on platinum. This is another picture of iron atoms on copper substrate, and it can actually enable us to image small objects that are not possible to image using the optical microscope. So our development of the understanding of the atom structure was not just an abstract job that we're trying to do for the fun of science. It actually enabled us to develop really important technologies like the electron microscope, as we pointed out here. And that all is based on de Broglie's idea of the wave nature of the electron, or the dual nature of the electron.